Hello and welcome to the structure part of the P47D presentation. Basic structure. The airframe is divided into separate components. The central components, which is the fuselage, the wings are attached to it, and then the tailplane. When designing an airplane, it is kept in mind to achieve as less weight as possible for maximum performance. But being light is not everything. It needs also to be strong so that it can withstand all the loads it is subjected to during the flight. For this, various manufacturing methods are used, and also many materials may be used so that the weight can be reduced and the higher strength to weight ratio can be achieved. Types of airframe construction. Wooden construction used early on with wood and thin wood sheets or fabric for skin. Wire-based structures with wires running along the structures to reduce the weight. Uh, Monocoque structures, the skin is thick and strong enough to carry all the loads with no airframe. Semi-monocoque structures, the airframe, which is made up of hoops, is used with stringers and longerons running across it with skin on top of it. And in this case, semi-monocoque, stress skin and the airframe, the load is divided in between them. So a lighter airplane is achieved in case of semi-monocoque. The fuselage, ingenuity and new ideas were achieved when designing the P47D with a lower frontal area, which gave maximum aerodynamic performance, but it also came with a price such as less fuel carriage, etc. The fuselage carry all the payload. It is a central body to which all the parts are attached to. It must be able to resist the bending moments from the lift production and the weight. And if this is the wing and this is the CG, so the bending moment in the fuselage, and also the torsional loads from the rudder and the fin, and cabin pressurization loads, which is from the differential pressure when the plane is traveling, especially at high altitudes. So it's the differential in pressure between the atmospheric and the internal pressure. So the pressure, the loads are on the skin or the airframe in that case. It is made up of frames, series of frames which give it a cross-sectional area. Bulkheads, closed frames here in the front and the back, and stringers which run along the frame to give it strength to the frame, and skin when attached and bolted to the stringers and the frame. So the load is, again, it is a semi-monocoque structure, so the load is divided in between them. Airframe goes the fuselage goes under fatigue, which is cyclic loading, depends on the intensity and the magnitude of the load and the frequency of the load. Wing construction. The wings consist of spars and ribs. So the ribs are aligned parallel to the wing, to the surface of the wing itself, perpendicular to the surface of the wings itself, and the spars go spanwise into the ribs. The stringers overlay the spars and the ribs, and the bulkheads, which are actually closed ribs. So the spars carry all the shear forces and the bending moments. The stringers are attached to the skin, run spanwise, and stiffen the skin. Effectiveness of the load carried may be increased by closely rivets or bonding along the entire length. Control surfaces. There are two main spars and three auxiliary spars in this airplane. So each control surface is actually joined by a steel hinge to one of the auxiliary spars, three auxiliary spars in the wing. The aileron, the flaps, materials. Earlier wood with fabric was used. Nowadays aluminum with copper aluminum alloys are used. Copper, aluminum, zinc, aluminum, etc. Aluminum itself is not used because it's not strong enough. The alloys are lightweight. Avionics. In avionics, different materials such as gold, etc. are used in the instruments, electronics of the airplane. Plastics in the upholstery, etc. It really depends on the designer of the airplane, the upholstery, but it is also aimed here to minimize the weight. Steel are used where localized strength is needed. the ailerons, hinges, etc., where local strength is needed, and composites, which are nowadays are very much research is done into calculations. So the scale of the plane was obtained by dividing the actual wingspan by the model's wingspan, 12.8 divided by 1.6, and it was obtained eight times the original. The model was actually 8 times reduction in the original size of the airplane. The CL was scaled down because CL, the airframe dimensions are the same, so the CL doesn't actually change. The cruise speed was also scaled down from the actual airplane, so it was 8.44, and the max speed was 24.2 meters per second, which is actually reasonable, and RC plane easily achieved these speeds. The lift was then obtained half rho v square SCL from this formula. So half the sea level density, the v square, the cruise speed v square, and the wing area from the model, and the CL, which we obtained by scaling it down. So this is the wing, this is where lift acts, and this is the distance which can be obtained by the geometry of the dimensions. So this distance is where this distance is the mean aerodynamic chord from the root, and it can be obtained from the formula. So if this is the distance and this is where the lift acts, so maximum lift can be calculated from half rho v square SCL. So that's half into 1.225 into 24.2 into 3.48 into 0.69, and we obtain 861 Newton for the lift, where rho is the density, velocity is as, surface area is s. And root chord is the root chord, and the distance is now obtained from that formula. This is the root chord, and this distance from the root chord is obtained by this formula here, which is obtained to be 34.2, which is actually very reasonable from the geometry of the wing itself. If that's the rib, one of the rib number 5, and this is the cross section of it. So those squares are where the spars go, under it and over it, under it and over it. And the second moment of area is actually calculated from, if this is the central axis and this is the y-axis, so parallel axis theorem is used to calculate the second moment of area of these spars so that the loads, the bending moments, can be calculated. So IA, which is now being calculated for these spars, it represents the resistance to bending. I calculations are which represent the carriage of the load transmitted by the wing. For square bar, it is the dimension, which is this breadth 4. The index is 4 because and it is divided by 12, which is the formula. And this is the parallel axis theorem is used here. So this is the distance from the reference axis, and again the breadth squared, and we obtain these 4 values for IA, for IA1, IA2, IA3, IA4, and then the 4 values are added and substituted in this formula, my over I. So that's the moment, which is the lift, into the distance where the lift acts, which we obtain 34.2 from the geometry. 3.5 is if the thickness of the root is 7, so 3.5 is the center of that thickness where the lift is actually acting, and 2.62 is the sum of i's, so we obtain the bending stress to be 3.92, and the shear stress is calculated by this formula, and it is obtained to be 2135 pascals. The shear strain is actually shear stress over shear modulus. So if shear stress was 2135, so the shear modulus for the spruce is 1200000, and the shear strain is actually the difference in length the difference in length in the spar when it is bended For example, if this is the spar, when it is bended, the difference in length here when it is bended upwards is obtained to be 1.77 into 10 to the minus 3 meters, which is in micro. Build. So 11 weeks were given us, and we had to make the most out of our time. The model airplanes were divided into the group. So one person was working on the fuselage, one person was working on the wing, etc. I mainly worked on the wing and the tailplane, and because I enjoyed actually making the curvy edges, making it aerodynamic, etc. And also did some skinning. So initially the papers, these maps were given to us. So all the parts were aligned to the map. So these spars are actually spars of the wings, and this is the wing diagram, and these are all the ribs. And so it was kept on the paper, all the spars and the ribs were also. And then we actually taped at first the spars with the ribs to give us an initial shape. We didn't glue because we needed to actually finalize the shape itself. So all the spars and the ribs were taped here. So a wing was actually made. So I actually contributed in this part as well. And as you can see, the tape joints, the spars and the ribs. So the tape joints are here. And these are the front edges of the wing. First, one edge was made by the diagram in the map, and the second, this edge was kept on this, and then it was cut, so that two edges were now made for different wings. And the back edge was this strip, and then the front curve part was then cut separately and stick to it for additional strength. The wingtips were made from 3 blocks of wood glued together by me, and then cut and then sanded to give the shape, aerodynamic shape to it. So this is actually the process I went through. The wood block, as you can see here, and then it was sanded and it was cut with this paper mark. I actually put it on it so that I know the dimension it needs to be cut to, and then it was sanded smoothly, and as you can see, the wingtip was made. So this is actually the tail plane, the horizontal stabilizer, and one of these ribs here, sorry, not ribs, one of these things here was actually broken, and I needed to make them anew, so I made them myself. The tips were also made similar way to the wingtip and glued together, 2 pieces, and then cut, and as you can see, smooth, nice, sanded for aerodynamic. And also the front edge was made into a curve so that it needs to be aerodynamic as well. And I also did some skinning over it with wood sheets, glued as well. This is the rudder. The rudder, it was square. It was having square edges as well, so I made it, cut it, and made it aerodynamic. So that's the fin ready, as you can see, skinned with all the front edges. I did. This is the bottom part of it, as you can see. That's the without the skin, and also there's some skinning on the flaps and the trimming tab. Some skinning done on the fuselage, also with my teammates. So that's it. That's my presentation for the P-47D Thunderbolt, and that's all my team. Thank you for listening to me, and thank you for giving me this chance.